Right, so we have discussed about self-inductance earlier. So now let's look at the mutual inductance. Yeah. Okay, basically for mutual inductance, you need to know what is the concept of the mutual inductance. So mutual inductance basically the flux. Yeah. We would like to calculate the flux at the second coil. If you still remember at the previous lecture, we are discussing about the flux that is happening around coil number 1, which is at this one. Okay, the one at this part. Okay, the one that is no related with the flux linkage, which is on the next flux. Yeah. So for mutual inductance, we want to look the flux that is linked to the second linkage, yeah? Which is basically at coil number 2. Okay, at coil number 2, whereby the flux, yeah, is produced. Yeah, the flux that is happening at coil number 2 here is the resultance of flux that is produced from the primary winding. So that is what we call as mutual inductance. All right, and we also would like to calculate the inductance value. All right, which now the flux, yeah, is we need to consider the flux that is linked from the primary winding. Okay, and the current source is still from here. Okay, the current source for this mutual inductance, it still came from coil number 1. Okay, because we supply the current at coil number 1. So we want to find or we want to get the value of the inductance now with the linkage flux in coil number 2. Alright, so that is what we're going to discuss, or we want to look further in this lecture. So a short review, okay, a short revision, okay, about self-inductance. So self-inductance is the inductance that is produced at coil number 1, okay, which is only we calculate, yeah, the value of flux at coil number 1 only, right? And the flux is basically is generated or caused by the current I1. And if we look into the equation, it can be write as N1 flux that is happening at coil number 1 is equals to the value of inductance at coil number 1 equals to current multiply with the current value at coil number 1. All right, so this is the supply current. So let's look what is the mutual inductance. So mutual inductance is more or less same as the concept of self-inductance, but now we have another terms, okay, where we are now considering the coil number 2, okay, the turns that happening at coil number 2. So due to the flux that is produced at coil number 1, okay, the flux will be linked to coil number 2, and that particular flux here, right, that particular flux will then be generating or will producing current of I2. Okay, so current of I2 is not the supply anymore. Yeah, so current of I2 is the resultance of the flux that is coming from coil number 1. Okay, then it will produce I2. Right, so current I1 will produce the magnetic flux, which will link to coil number 2 due to the flux linkage. All right, so mathematically, flux linkage in coil number 2 will be can be represented as the equations here. So if we want to convert into normal mathematical equations, so it's gonna be coil number 2, okay, number of turns at coil number 2, flux that is happening from flux linkage. Flux 1, 2 is the flux linkage in coil number 2 due to current I1. Alright, is equals to L2, which is inductance. Alright, there's no more L2, but it is written as, in order, since that this is now a mutual, it will be write as M. Okay. Yeah. It will be written as M12 I1. Okay, M12 I1, because I1 is the supply. So if we want to rewrite, as I mentioned earlier, if we want to calculate the value of the mutual inductance now, it is equals to N2 flux linkage 1, 2 divided with I1, okay, the current. So M is representing the mutual inductance. Mutual inductance. Okay. Okay, now let's look into the example, right? So example here, example 1, consider two singleton coplanar concentric coil of radii. It's given the radius is R1 and R2. So there are two concentric coils, yeah, coplanar, right? So it is lies on XY axis lah. It is coplanar, yeah, planar, where radius of R1 is much more larger than radius of R2. Okay, R1 loop carries current of I1 in clockwise direction, and we need to determine the mutual inductance. Okay, so they mention specifically we need to indicate or determine the mutual inductance between the two loops. So if we can draw in terms of structure, if we can illustrate the structure, okay, R1 is much more larger than R2. So R1, this is going to be our R1, sorry, R2. Okay, this is R2. Okay, wait, yeah, I try to draw a bit larger so that we can write R2. So this is our R2, because it is much more smaller, and this is our R1. R1 is larger, basically more larger compared to R2. Okay, so this is our R1, where R1 carries a current of clockwise direction. So it carries a current of clockwise direction, so it's gonna be on this direction, yeah, the current. So this is our I1. Okay. Alright. So basically, in order to get our objective is to get the mutual inductance. So M mutual inductance between these two concentric planar coils, we're gonna be N2. Okay, flux from 1 to, okay, divided with I1. Okay, and to get this, flux can be calculated. So we know flux can be calculated by using the, so number of turns they didn't mention, so we assume number of turns is equal only 1 lah. Yeah. Alright, so what else? Yeah. So we need to find the flux. So flux, we're gonna be flux 1, 2 is equals to the same of flux M, right? So it can be calculated by using the B dot ds, same as before. Okay, B dot ds. So B can be assumed ataupun can be determined by using the mu naught H dot ds. So this is our directions, okay, in order to solve this particular questions. So to solve this, let's recall, if we can recall our Biot-Savart. Okay, let's recall our BSL, Biot-Savart law, where we have a cylinder disc, okay, and we need to find the H at z-axis here. We need to determine H at z-axis, which is given the coordinate as 0, 0, z, and the radius is given as a, if you still remember. Okay, and the directions of current also clockwise direction. Okay, if we still remember, we able to determine in order to get this, h can be determined equals to integrations of I dl cross with r over 4 pi r cubic. All right, and let's recall. Okay, I think most of you guys perhaps still remember. Okay, I a, okay, the radius is given a. Okay, dl we're gonna be on phi direction. Okay, on phi direction, and the r we're gonna be, r vector we're gonna be a at negative r direction. Okay, plus with z on positive z direction, right? And we can ignore later, yeah. This r can be ignored later, okay, due to the symmetrical effect. Okay, due to the symmetry effect, we can ignore this, right? And divided with 4 pi a squared plus z squared, z squared 3 over 2. Okay, if you still remember. Okay, and if we solve this, we are able to get the answer as I, the h, we're gonna be I a squared over 2 a squared plus z squared 3 over 2. Okay, 3 over 2 on positive z direction. So this is what we have able to obtain in previous lecture. So if you not very sure about this, so please remember or please revise again what we have learned in previous BSL. Right? So now the radius, we want to relate what we have learned in BSL before with these questions. So in these questions, okay, in BSL, the radius is given as a, right? But now in our cases, the radius is given as r1. So we can substitute actually a into r1. And what is the value of z? Z is somewhere that is located around at z-axis, right? The position of h that we want to determine, which is located at z-axis. In this case, in this our example here, in this question here, there is no z-axis is given. Okay, there is no z-axis is given, so therefore our z will gonna be 0. So if we can substitute this information into this equation, we are able to obtain the value of h is equals to I r1 squared over 2 r1 squared plus 0, right? Z is equals to 0, which is 3 over 2 on z direction. And we can further simplify this equation to become I r1 squared over this 2 and this 2 can be cancel each other, so it will become 2 r1, yeah, 2 r1. Okay, so this 2 and this 3, so it will become r1. There gonna be no r1 up here, yeah. Okay, because this r1 and this r1 can be can be divided, yeah. So it will become I1 over 2 r1 on z direction. Okay, ampere per meter. So these are the value of h that is now will be generating, or that will be generating at this particular, for this particular example. Okay, for this particular example. So due to R1 is much larger than R2. It's very, very large compared to R2. So therefore, R2 can just be seen, okay, because of R1 is much more larger compared to R2. So therefore, R2 can just be seen as a point. As a point. Okay, because of why? Because of R1 is much more larger compared to R2. So we can look R2 just as a point. So therefore, okay, from here we can calculate the value of flux. Okay, so the value of flux will then become, okay, so R2 is as a point. So therefore we can neglect the effect of R2 to H. Okay, we can effect the effect of R2 into H field. So that's why we assume it to become as a point. Yeah? So what make our assumption valid is because R1 is much more larger than R2. If R1 is not so, R1 and R2 is almost the same radius. So you cannot assume R2 as a point, right? So they're going to be effect of H field, right? So therefore, in order to get the value of flux, so it's going to be mu naught, okay, mu naught H1 we're going to be the value of H that we have calculated earlier, 2R1 on a Z direction. So our DS also should be in the Z direction. So it's going to be R dr dphi on Z direction, right? So on, if we can proceed the calculation. Right, so we can get mu naught 2R1 I1 Z we're gonna R we're gonna be from 0 until R okay, so the radius of R now, R1 or R2? Okay, so the radius of R1 or R2? Okay, this we're gonna be d phi, right? So d phi no problem, yeah, the limit is 0 until 2 pi. So now where is our limit of R? 0 until R or 0 until R2? Okay, although we just assume R2 as a point, okay, R2 as a point, which R2 as a point will not affect our H. However, the flux that is produced now, our flux now is equals to mutual flux, right? Flux 1, 2, right? Flux, mutual flux, right? So the mutual flux for here, okay, since that the source of our H field, now is R1. Okay, the source of our H field now is R1. So therefore, the mutual inductance, the flux for flux linkage here will be from 0 until R2. It cannot be longer to R1, because if it is R1, there are going to be no mutual inductance. So mutual inductance, we know, right? It is linked from coil number 1 to coil number 2. So now our distance in order to create this flux of flux linkage here will be from flux that is generated from the source, which is R1, our source, to R2. Okay, it's gonna link from R1 into R2. So therefore, that is why our limit for R, yeah, we're gonna be 0 until R2, because this is a mutual inductance. Okay, so therefore from here we are able to obtain the value of psi m, which is the linkage, yeah, is equals to mu naught over 2 R1 I1 R2 squared and 2 pi. Okay, so whereby these 2 and these 2 can be cancelled out, right? Okay, oh sorry, there is R1 R2 over 2, right? So this 2 and this 2 will be cancelled out. So therefore, we are able to determine the value of psi m, okay, will be equals to mu naught over 2 R1 I1 R2 squared pi. Okay, pi. So next, what is our direction next? We need to divide with I1. So this one, we just divide with I1. Okay, so we can cancel this. So later we will get the mutual inductance. For this case, M is equals to mu naught over 2 R1. So this is 2, yeah. R2 squared pi in Henry. Okay, so this is our final answer. Okay. Alright, now let's look at our next example, which is example number 2. A long straight lightning conductors lies in the same plane as a rectangular metal window frame. So the window has a side of 1 meter and 1.5 meter. So it is rectangular, right? 1 meter and another side is 1.5 meter. So the shorter side are parallel to the lightning conductor, and the nearest side is 0.5 meter from it. So if we can draw or illustrate the structure somehow going to looks like we have a lightning conductors. So this is the lightning conductors, okay, where it will carry currents of I, yeah, by default it will carry currents of I. Okay, and then we have a rectangular metal window. So we have a rectangular metal window where the shorter side parallel to the lightning. So this is the shorter side. Okay, so this is the shorter side, right? So this shorter side is parallel. Tak nampak. So this is the shorter side. So this shorter side is parallel to this lightning. So this is the lightning area. Okay, so it is parallel. Then it somehow it gonna looks like that lah, right? And where it says the nearest side is 0.5 meter. So meaning that the two between these two distance, yeah, it is 0.5. It is separate with 0.5 meter. So the longer side is 1.5 meter. And this side is given, the length is 1 meter. Okay, now, so to get what they ask, they need us to calculate the mutual inductance. So mutual inductance, we're going to be 1, 2 is equals to flux of 1, 2 divided with I. Okay, basically there is an n, right? But then n is not given here, so we just assume n is equals to 1 lah. Alright. If they mention specifically how much the number of turns, then you need to consider the number of turns. If it is not given, so we just assume as n is equals to 1 lah. Alright. So the flux, we're gonna be the flux linkage that is produced by this current. Okay, by this current, and it's gonna be divided by the current. Okay, so now, so from here we can determine the psi m is equals to b dot ds over I. Okay, I is the I that is coming from the lightning conductors, yeah. So from here we need to know the mu naught h dot ds over I. So mu naught h, which one that will produce the h? So this one, yeah, that will produce the h field. So we can use our knowledge that we have learned in Ampere's second law, ACL, for a very long conductor. So it will equals to mu naught I over 2 pi r, right? 2 pi r. So what is the directions of our h? So if we use the right hand rule, the directions of h will gonna be going backward, yeah, going backward. So it's gonna be on negative x direction. Okay, negative x direction. If we assume this is gonna be on z direction, this is going to be on X direction, this is going to be our Y direction. So it's going backward. Okay, it's going backward, so it's going to be negative X direction. Our ds will going to be the ds that is coming from this particular window, right? So it's going to be dy dz. So since that our h is in negative x direction, to make it simpler, we take it as same negative x direction. If you are taking positive x direction, you will then get your answer, your flux in negative, yeah? Positive, negative, you will get negative later on. So flux positive or negative, it doesn't matter. Okay, also acceptable, yeah, divided by I. So now our R. So R, we know R is applicable for a cylindrical. So there is a combination of cylindrical and Cartesian here. So what we can do is we can convert the cylindrical from cylindrical into Cartesian. So if we can see R is basically the distance between, okay, the distance from here to here, the one that is producing the H field to our interested area, okay, to our interested area. So if we can see, it is actually separated in Y direction. So R can be, okay, R can be also rewrite as Y direction, okay, because our rectangular window here is located somewhere at positive Y direction, right? So therefore, so now in our calculation, we only have Cartesian only, yeah, I over 2 pi y. So negative negative are going to become positive. So dy dz divided by I. So if we further expand, so we can bring mu naught 2 pi 1 over y dy. Another one is dz. So the limit we're going to be, our y limit will be from where? From 0.5, it start at 0.5 until 1, until 1.5, right? 1.5 plus 0.5 until 2. Okay, because the distance of the rectangular window with our source is 0.5, right? So z will become 0 until 1, the height of the window. Okay, so if you further, you're able to calculate the value of M for the mutual inductance. It will become mu naught over 2 pi, okay, mu naught over 2 pi ln 4 Henry. Alright, okay, so this is basically what mutual inductance is related all about. Okay, so what you need to know is you need to know where the source is. Okay, usually the one that is carrying current will going to become the source, and the flux, please remember, the flux is the flux that is from the source to our next point of interest, because it is a mutual, yeah, mutual inductance. Okay, so please remember. We have finished our inductance topic. Okay.